All right, so let's get right into it. We're going to talk about one of the biggest, maybe the biggest ambitions in AI research today. This whole idea of teaching machines how to build a model of the world, inside their own digital heads. But to really get why this is such a huge deal, we first have to wrap our heads around this really interesting paradox. I mean, on one hand, AI can do some absolutely mind-blowing things, right? It can write code, create stunning art, and beat the best of us at super complex games. But then, and this is the weird part, these exact same super smart systems can just fall apart. They can fail in the most bizarre and, frankly, unexpected ways the moment they run into something just a little bit different. So that really brings us to the core question we're tackling today. Why? Why are these incredibly powerful AIs so brittle? What fundamental thing are they missing about the world that you and I just, get without even thinking about it? Well, the answer, it turns out, is buried deep inside how they actually learn. All right, so this gets us to the first big piece of the puzzle, AI's blind spots. And it turns out that for all their impressive abilities, a lot of today's AI systems are basically working with what researchers call a bag of tricks. Now, this bag of tricks has a more technical name, a bag of heuristics. And really, all that means is it's a huge collection of disconnected rules and shortcuts that the AI has learned from all the data it's seen. You know that old story about the blind men and the elephant, where one guy touches the tusk and thinks it's a spear, another touches the tail and thinks it's a rope? Yeah, it's kind of like that. Each one understands a tiny piece, but nobody gets the big picture. Nobody understands that it's an elephant. And that's pretty much how a lot of AIs work. They've got a ton of disconnected facts, but no single coherent picture of reality. And here is a perfect, almost scary example of this problem in action. Researchers did this study where they trained a big language model to give flawless driving directions for Manhattan. And you know what? It worked. It was perfect. But then they throw in a tiny, real-world twist. They blocked just 1% of the streets. And the model's performance didn't just dip, it completely cratered. And here's the key takeaway. It hadn't learned a map of Manhattan in its head. Not at all. It had just memorized a giant list of turn-by-turn instructions. So without that real internal map, a single roadblock was enough to break the whole thing. Okay, so if that bag of tricks is the problem, what's the solution? Well, this is where we get to the really big idea. An idea that's actually making a massive comeback in AI research. And that is giving the AI the one thing it's been missing all along, an internal world model. And a really fantastic way to think about a world model is like a computational snow globe. Seriously, it's like a tiny working simulation of reality that the AI can carry around inside its digital mind. And with this little internal model, it can suddenly understand context. It can predict what's likely to happen next, and it can reason about the world in a way that's just impossible if all you have is a bag of tricks. It can, metaphorically shake the snow globe, see how things might play out, and then decides what to do. And what's crazy is this isn't some hot new idea dreamed up in a lab last week. Nope. This concept was first proposed way, way back in 1943 by a psychologist named Kenneth Craik. He argued that the reason we can function is because we carry a small-scale model of reality in our heads. It allows us to, in his words, try out various alternatives and act in a much safer, more competent way. I mean, he was talking about the human brain, but he could have been writing the blueprint for the next generation of AI. And this idea has had such a fascinating up and down history. Back in the 60s, early AI researchers tried to build these simple handcrafted block worlds. But then, in the 80s, a very influential roboticist named Rodney Brooks came along and said, forget that. The world is its own best model. And for a long time, the whole field kind of moved away from internal models. But now, it's back in a huge way, all thanks to the power of deep learning. The goal now isn't to handcraft these models, but to have the AI learn them all on its own. Okay, so that covers the what and the why. But now for the really tricky part, how? How in the world do you actually teach an AI to build its own computational snow globe from scratch? Well, let's look at the three main ways researchers are tackling this right now. So it really breaks down into these three key approaches. The first is what's called embodied learning, which is basically learning by doing, but inside a virtual world. The second is all about developing abstract thinking, like an intuitive sense of physics, just from watching videos. And the third is about giving it a head start, or pre-training, by using all the human knowledge we already have. So let's start with that first one, embodied learning. It's a simple idea. Let the AI learn by doing things, But, and this is the key, it does it all safely inside a super complex simulation, like this one called AI Habitat. In here, an agent can just explore, try to navigate, pick things up, and the real magic is the speed and safety. It can cram what would be years of real-world trial and error into just a few minutes, all without ever breaking a single thing in the real world. And you might be wondering, okay, but how well does this actually work? Well, check this out. In one pretty stunning experiment, an agent trained this way was dropped into a totally new virtual environment it had never seen before. Its only job was to get to a specific coordinate, and it was given a virtual GPS and compass. The result? It had, wait for it, 99.9% accuracy. That's just insane, and it proves that these simulations are an incredibly powerful way to build really robust skills. Okay, so the second big approach is about teaching an AI to understand the world just by watching it. And to really get this, we got to compare two different methods. Over on the left, you have the old way of doing things, learning in what's called pixel space. This means the AI literally tries to predict every single pixel in the next frame of a video. As you can imagine, this is wildly inefficient. It burns so much energy trying to predict totally irrelevant stuff, like exactly how every leaf on a tree will rustle. But the new approach, over on the right, works in something called latent space. And there's this model called VJPA that uses this latent space idea in a really brilliant way. See, instead of predicting every pixel, it just learns to predict a more abstract idea of what's going to happen next. It focuses only on the important stuff. And after watching tons and tons of videos, it starts to develop this intuitive physics. It's a lot like how a human baby learns, you know? It can watch something happen and get a gut feeling for whether it makes sense physically or if it's just impossible. You can see it here. It learns to be surprised when something happens that shouldn't. And the results? I mean, they're just staggering. There's this test called IntPhys, which is specifically designed to measure this kind of physical common sense. VJPA scored 98% on it. Think about that. It can spot physically impossible events almost perfectly just by watching videos. Nobody ever sat down and taught it the laws of physics. All right, so this research is obviously fascinating, but let's talk about the real-world payoff. What's the point? How does an AI that can navigate a fake house or tell that a video of a ball looks weird, how does that actually help us build smarter AI in the real world? Well, this is where everything connects, in a process that researchers call sim-to-real. It's exactly what it sounds like. All those skills that AI agents learn in the simulation, they're now being successfully transferred over to actual physical robots. So a robot can spend, say, thousands of hours learning how to grab different objects in a virtual world, building up that internal model, and then it can use that knowledge to pick up real objects it's never seen before. It's the critical bridge between the digital practice room and the real world. So let's just pull this all together. Why is building these world models such a game changer? The benefits are just huge. First, you get robustness. You get an AI that doesn't just break when it encounters something new. You get reasoning, the ability to actually plan ahead and think through the consequences of an action. You get safety because the AI can predict an unsafe outcome before it happens. It's also more efficient because it can learn way faster with less data. And maybe most importantly, you get interpretability. This could finally give us a way to peek inside that black box and get a better sense of what the AI is actually thinking. Which brings us right back to that big question we started with. We asked why our most powerful AIs are often so fragile. And the answer really seems to be that they're missing a coherent internal model of the world. But now, for the first time, researchers are really making progress on teaching AIs how to build one. So the final question is this. Are these computational snow globes, these little internal simulations of reality, are they going to be the key that unlocks the next truly revolutionary level of artificial intelligence? You know, based on everything we're seeing, it's definitely one of the most exciting and promising paths forward we've got.